Modularization is a concept where source code is divided into modules. A module, otherwise called a library, makes specified data types and functions available which serve a specific purpose. For example, the number 1 is an object of the type integer. "1.0 is an object of the type float, and true or false objects are of the type bool. These are native Python objects. What then is the type of an RFEM6 model object, or of a node inside RFEM6? That's where libraries come in. Here we define classes needed to fully describe and handle RFEM6 objects and their parameters. Furthermore, they contain functions which help in working with these newly defined object types. Another example for a library could be the math library. To utilize the math library, I use the keyword import and the name of the library math. With that defined, I can access, for example, the sign function by typing in math.sign. There are other ways to import libraries, for example, from math import star, which negates the need to type the name of the library in the beginning of each command. Or from math import, and here if you want to access specific classes of a function. Your chosen way of importing libraries is a matter of preferred style and intention. In the Python high-level function library, which we obtained in the previous video, there is this distinct modularization of .py files, which contain the aforementioned classes and functions. The structure of the folders and files follows what we see in the main graphical user interface of RFEM6. For example, in RFEM6, insert basic objects nodes is mirrored in the folder structure of the repository. Let's see how to access this in Visual Studio Code. Where you store your code is an important thing to note, as it affects how to read in libraries. For simplicity's sake, let's save a Python script in the root directory of our cloned repository. Let's say now I want to access the node library. If I type in import node and try run that, it returns an error saying no module named node. This is because Python is searching for node.py in the folder where the script is saved. In order to help Python find the library, we need to show it where the node is saved. This can be done with concatenating the subfolders with a dot. So here from rfem.basicobjects.node, and notice the code completion as we were typing. Now we can define a standard node with a similar logic and procedure as one would do it in the RFEM graphical user interface. This is a good point to note that the workflow we need to define a model through Python is no different to modeling a structure manually in the RFEM graphical user interface. The algorithmic breakdown is the same. Define two nodes, lace the nodes with a beam element, where we define the section of the beam and the material it is comprised of, define support conditions, etc. This will be covered in detail in the first example of the cantilever beam. Some key points to summarize: the folder structure and accessibility of classes and functions mirrors what you see in RFEM6. Where the Python script you're working on is saved in relation to the high-level functions is extremely important and affects how to read in the libraries. The simplest way is to save your Python script in the root directory of the high-level function library. If for some reason you want to save your script elsewhere, you need to manage Python's current working directory. This can be done with the OS module and the functions get current working directory and change current working directory. With this overview, we can now jump into our first example.